We're going to start out by looking at something called EMF versus terminal voltage. EMF, I mentioned previously, that was what Volta called the voltage. It stands for electromotive force, but most physicists don't really like calling that a force because it's not, but they're okay using the abbreviation EMF. We'll also look a little more in detail at resistors in series and parallel. I've already kind of mentioned how to deal with those in class, but we're going to look at it formally in this video. So this idea about EMF versus terminal voltage has to do with batteries, and up until this point we've ignored any internal resistance in batteries. We've had circuits that had batteries and resistors, and we just treated that resistor as all the resistance that there is in the circuit. Well, it turns out that real batteries always have a little bit of internal resistance, which is what we're going to call lowercase r in this situation. And you can treat that internal resistance as being in series with the battery itself, which is what we're going to call the EMF in this particular situation. And then the terminal voltage is what we are calling VAB. So if we put a voltmeter here, that would give us the terminal voltage, which may or may not be the same as the EMF here internal to the battery, essentially the voltage of the battery if there were no internal resistance. So if nothing is hooked up to your battery, there's not going to be any current flowing. The voltmeter has really high resistance, so you essentially have zero current. And if there's zero current, you don't have any voltage drop across this resistor. Or if you think about this equation here, if I is 0, then IR is 0, and the terminal voltage will read the battery voltage, the EMF. This is sometimes called the open voltage. Now, if we had a circuit hooked up to this, say, I don't know, some resistor down here, a light bulb or something, we would still connect our voltmeter here to the terminals to read the terminal voltage, but now we're going to have some current flowing through that resistor as well as through this resistor here. And what that's going to do is this is no longer zero. And so if we find this voltage drop across that internal resistance of the battery, we have to subtract that from the EMF of the battery. And so the terminal voltage, the actual voltage you get to use, is going to go down a little bit. And the bigger the current, the bigger the voltage drop across that resistor. So the more your EMF will be lowered. Alright, let's look at a quick example. So here I have a circuit where this essentially is my battery, and it's got some internal resistance to it. It also has a voltage to it that we're going to call the EMF, and we want to find the current in the circuit. To do that, we just treat this as a battery like we used to without resistance, and in a circuit with two resistors in series. So all we have to do is apply Ohm's law, so this is for part A, where the total resistance here is going to be 65 plus 0.5, and then our voltage here, that is the EMF. So I guess we could have written EMF here. So we end up with I equals 12 is our EMF over 65 and a half, which gives us 0.18 amp current. Now that's the current through each resistor because there's only one current throughout this circuit. There's no branches, nothing in parallel. So there is only one current for the total circuit as well as for each component. So for part B, we want to know the terminal voltage, so VAB, which is our EMF minus I times little r. So that's just 12 minus the 0.18 current times 1/2. So it doesn't lower the voltage by a whole lot, but it lowers it by something. Okay, the last part here, we want to look at the power dissipated through each part of our circuit. So the power for the big resistor is I squared times the value of the big resistor, 0.18 squared times 65, which works out to be 2.18 watts of power. we have essentially the same equation for the small resistor. It's going to be 0.18 squared times 0.5, and this works out to be significantly less. So once again, the effects of the internal resistance of a battery are usually minimal, but they are there. In fact, if you've ever seen, I mean, newer cars are more complicated with their electronics, but if you ever seen an old truck with the headlights on before somebody started it, when they go to start the car, that starter takes a lot more current, and so that drops the battery voltage, which is what dims the headlights when you're starting that car. And as batteries get old and die, what actually happens is that internal resistance increases quite a bit, and then they're no good anymore. Now we're going to look at resistors in parallel and in series. In this case, they are in series, and we know that because there's only one path for the current to flow. All of these resistors have the exact same current flowing through them, so that is one of the definitions of being in series. So you really need to remember the difference between series and parallel. Current is always going to be the same when you have a series components in series. The thing that's going to be different is the voltage. So voltage will be different. Essentially, the voltage drop across this one plus this one plus this one have to add up to give you the total battery voltage here. So we can write an equation expressing that. Sum of these voltages has to equal the battery voltage here. And then if we substitute in I times R for each of these voltages, that since the I's are the same, we don't need subscripts there. The R's will be different. And we can go ahead and factor out that I, and we get to R1 plus R2 plus R3. And then we can call this sum here the equivalent resistance. And we can go ahead and use this part of the equation here, cancel out the I's, and we get that the total resistance, or the equivalent resistance, is just the linear sum of the resistances of the individual resistors. And by equivalent resistance, what we mean is that, oh, it looks like I drew over that area. There we go. Is that if we replace those three resistors with a single resistor, we would get the same current going through the circuit. We would get the same overall power being dissipated, and essentially everything would be the same. Alright, now to look at a parallel circuit. Parallel. The reason that we know this is parallel is because there's more than one current. The total current coming from the battery here splits into different branches of our circuit here, and so that is one of the definitions for parallel. So for a parallel circuit, we know that the current is different in each component, but the thing that is the same is the voltage, because all of these resistors are essentially connected right to the battery, so they have to have the same voltage, which will equal the battery voltage. Now we can follow similar logic to adding up the voltages in a series circuit, but with a parallel circuit we're adding up the total currents. So these three currents have to equal the total current coming off the battery. So if we write an expression of that and then substitute V over R for all of these things, since I just mentioned that the voltage is the same, we don't need different subscripts here, and these voltages will all cancel out, and you end up with this expression. So opposite rule of thumb for adding resistors as for capacitors, right? If these guys are in parallel, you add them in reciprocal. If they're in series, you just add them directly, and you do the opposite for capacitors. And again, this equivalent resistance is the same idea as if I replaced those three capacitors with, those three resistors with a single resistor. We'll do a quick little conceptual example here. So if we have light bulbs that we can either connect in series or in parallel, and we want to figure out which of these will produce more light. Well, we're not changing the resistance of the light bulbs, so that is fixed. What we are doing is we're changing the voltage and the current running through it. So in this case, the total voltage drop across both light bulbs has to equal the battery voltage, the terminal voltage. And in this case, each light bulb will have the full battery voltage across it. So the parallel one, they're going to have a higher voltage. They're also going to have a higher current in this case, because here the current essentially gets slowed down by the extra resistance. and it doesn't here. So the parallel configuration will produce more light. Which way do you think that they are wired? Well, if you've ever noticed a car that has a single headlight out as opposed to both, then you would know that they are wired in parallel. Because if they were in series, if one went out, that would be an open circuit and the other one would have to go out too. They used to make Christmas light strands that were like that, where one single bulb was out and the whole string would have to go out, and you would search through replacing each bulb one by one. It was a big pain. But then they wised up and said, oh, why don't we just put these in parallel so you can see the one that's out and replace that one. Alright, see you next time.